by early, just go back. So first few months of 1995, we were getting down to 200 nanokelvin, which at that temperature was the lowest temperature ever observed. This evaporation was working well. Things were going great. I was really excited. We went to a conference in Toronto. It was the American Physical Society meeting. It was held jointly with the Canadian Society that I took my student. Carl went also. We were gonna it was gonna be our big triumph. We didn't have Bose condensate yet, but people were gonna see this, and they're gonna be impressed. We thought. So I went and this was an earlier era, and you would put these sort of acetate slides up on an overhead projector, and then you put a piece of paper like this, so you could sort of block out. So I said, oh look, this cloud is 180 nanokelvin, this cloud is 35 nanokelvin because it's smaller, and they could see I'm going to show them something else. This was back in the day when you would use this sort of this effort for building up suspense until people gradually want to leap out of their seats and throttle you, just as you want to throttle me. I showed this picture, and there was people started groaning because they realized people in the know saw these diffraction rings here. That's what happens when you try and take a picture using laser light or something which is too small of an image with your lens. You just see these rings. So all you could really say about this particular cloud is that, well, it's colder than 35 nanokelvin, but we don't know how much, and basically these sort of funny rings pattern here means that you can't really see it. So we were pretty proud of that. But it turned out in that same session, there were two other groups from around the country that was also getting evaporation, also had very impressive evaporation results on the way to Bose-Einstein condensation. And it was really frustrating because it seemed like we had jumped directly from that part where everyone said, oh, it can't work, to the part where everyone said, oh yeah, of course that's going to work, and moreover, we're going to do it before you do. Where was the part where we were the conquering heroes or something like that? So it was it was exciting, but also like, okay, now we actually have to go make the thing work. Flying back from Toronto, sitting next to my student was sitting next to me on the airplane, Mike Anderson, who said, Eric, I don't think there's a lot of time left to piddle around anymore. I said, no, Mike, there is not a lot of time left for piddling around. If you've been piddling around, this would be a fine time to start. We got to get moving. So it was a tense time. It was, science is about pushing back the frontiers of human knowledge, and advancing the human spirit and so on. But it's a competitive endeavor, like a lot of things that people do, and you want to try and do it first if you possibly can. So we came back thinking, okay, we need somehow to take a picture of things that are smaller. What we did instead is we made the atoms bigger. The atoms, that white circle sort of represents like a little magnetic mole. What we did is we turned off the magnetic mole, and the atoms, which were hard for us to see there, flew apart. We waited for a little while, and now the wall on the side of the building, and you connect the two ends of it together, and it's full of the superfluid. If you could get it flowing around in there, they would flow around essentially forever. Superfluidity means no friction, no viscosity. It would be a very strange thing to happen. A Bose-Einstein condensate is a superfluid. We can't make enough of it to fill up a garden hose. And even if we did fill up the garden hose itself would be so hot that the condensate would boil away. So we need to do something else. We do it by studying vortices. And I just thought before I did that I showed you an older picture. This is some more modern picture of some of the people in my lab. Let's see, this is just standing out in the sunshine just outside the lab. Let's see, Matt, Chen, Eric, now I've lost it, Kevin, Laura, Tyler. That's one big issue with working with really big lasers is you do want to keep your arm out. That wasn't what happened. It was a lot less romantic than that. But yeah, can you imagine a laboratory accident cuts off your arm? That would be a story to tell. Let's see. So we don't have enough Bose condensate to fill up a garden hose, so how can we see that it's superfluid? We do it by studying vortices. Vortices don't happen in any kind of fluid. They happen in air, they happen in water. This particular vortex is an enormous vortex called Mitch. It's out in the Gulf of Mexico somewhere. It's a hurricane. Hurricanes are vortices. What all vortices have in common is that the air flowing around, as you get closer and closer, the air flows faster and faster. And right in the middle of every vortex, there's a region of low pressure. In the hurricane, it's called the eye of the hurricane. In tornadoes, it's called the core of the tornado. Maybe the most standard vortex you're ever going to see is you're taking a bath, you pull the plug out, and you see that little sort of tornado thing go down the drain. That's a vortex. And sure, right down the middle of the vortex, there's no water at all. The pressure or density of water vanishes in the middle of a vortex. So those are all classical vortices. A superfluid, the vortices are a little different. So suppose you pull the plug out of the bathtub, and you got the water swirling down the drain, and then you take the plug and you put it back in. Suppose it just kept swirling.